Oh, someone said that.
Okay,
10 to 20.
guys, I've got 10 o'clock. It's good to see everybody. Welcome back. This is Thursday. I hope that your week is treating you pretty well so far. I know a lot of people have been having exams and crazy times. The month of October is kind of rough. We have no holidays and we have a lot of work to do. So anyway, we just have to take it one day at a time. Couple quick announcements. There is a homework assignment that I hope that you're starting on already. It's due tomorrow night. I'm gonna answer some of the questions during class today. I've already got a few on the board, and if you wanna add more during our break today, you can do that. If I'm not able to get to all of those problems on the sideboard, I will do one of two things. I'll either answer your questions during my office hours today or tomorrow. Or I'll just make a separate video of some of the answers worked out that you can watch later on as well. I've been known to do that too. But the main thing is to make sure that you actually do these problems. Be sure that you spend some time with it because this is a little more of the abstract material on vector spaces, and I find that people really need to sit with it a little bit. You have to put some time into this. You can't just expect it to automatically be learned without doing any work. So you are gonna have to put in some work on this, but I'm gonna be here to help you as always with that. After we get through tomorrow's homework, there is another one waiting in the wings for next Tuesday, which will be about spanning sets, a lot of stuff on this material that we're gonna cover today. So over the weekend, you can look at that and we'll talk more about that next time as well. So those are the immediate assignments that are on the radar for now. And then these are the office hours in the immediate future. I will be downstairs right after class today, if anybody wants to follow up with me there. And then after I'm done with all of my afternoon classes, I'll be back down there again at 5:30. And I'll be there all evening tonight, pretty much with the exception of a dinner break around 7. But I'll be mostly there, either in Zoom or in person. Feel free to stop by and talk to me. I've been really happy with all of the office hour activity. People have definitely been doing a good job of asking questions and coming in to get things clarified. So I hope you'll keep doing that. If you can't see me today and you want to talk tomorrow, I will be available in the evening for a little bit of time. I don't have a massive amount of free time tomorrow, as it turns out. But these are some extra hours I don't normally do. But because there's homework due tomorrow night, I'm going to at least jump in for a little while tomorrow. Oh, I should mention, these hours tomorrow is gonna be a Zoom only time because I'm gonna be actually off campus. So jump into Zoom if you wanna talk to me tomorrow about anything. You can also shoot me an email and I'll respond back to emails promptly as well. So any of those hopefully will be good ways for you to reach out to me and get help with anything that you need. Does anybody have any questions about that? I find that this material on spanning sets is a little bit challenging sometimes for people. I'm gonna try my best to make it as easy as I can today. I've gotten a little better at it over the years. I think I can do it. But just in case, I do have a document that I put together. I wanted to show it to you in our Canvas page. If you go to the files section, like always, there is a folder that we've looked at a few times called Special Handouts. And if I open that up, this is the one that has the vector space axioms in it. But there's also a document that I wrote up called Spanning Sets. This is what we're going to be covering today. This is a very short 3-page document that basically is a summary of what we're going to talk about right now. And it's got 9 examples in it. So if you need to read it again later, it's all summarized right here. I've even had students decide they didn't want to take notes in class because they just wanted to listen. And so what they did is they took this as their notes and used that to supplement the lecture. I also, if you don't like that, we can go to the pages section instead of the file section because I have additional videos, right? So if we scroll down, these are roughly in order of the book. You'll see that I've got spanning sets and linear independence, sort of a part 1 and a part 2 here. And there's even a 28-minute video crash course on spanning sets. So feel free to watch all my videos. You just have to make sure you promise me you click the like button if you watch one. Hopefully you like it, and that'll help grow my channel. Anyway, so One day I'll become a YouTuber, when I'm not so busy with everything I'm doing here. But that's that. So anyhow, let's get back to where we left off on Tuesday. We're talking about vector spaces, right? Capital V, these are the big universes. We've talked about M by N matrices, N by N matrices, polynomials, they can form a vector space. What else? Rn is like a classic vector space example where you have physics vectors essentially with slots. What's another vector space? Calculus functions, that was a vector space. So there's lots of these universes that we work in, and you're gonna see all of them on the homework assignments because I like to have people practice what the concept looks like in each of those universes. Right, so you'll see a lot of that. But the idea that I tried to pitch last Tuesday at the end of class is that we can actually make a lot more vector spaces than just those sort of big universes that we're starting off with. If we simply grab a handful of vectors, right, from whichever of those universes I want. So you just grab a bunch of vectors and you form their span. It doesn't matter what these vectors are. It could be as many or as few as you want from any type of universe that you want. You just form the span of those vectors, and the theorem will be that that will always form a subspace of V. It's guaranteed. It's not even you don't even have to check anything, right? So I will often put this on one of my exams. I'll ask you, is such and such a subspace of V? Yes or no? And if I put a question there that says span of whatever, you're gonna circle yes, right? Anytime you take the span of anything, you will always get a subspace. And remember that a subspace is just a vector space in its own right, sitting inside of V. Okay, so it's kind of a no-brainer. It's as fast as an answer as the null space of a matrix, right? I talked about that on Tuesday. Anytime you take the null space of any matrix, you automatically get a subspace. Right. Anyway, what is the span of this handful of vectors? I've reminded you here, it's just all of the possible linear combinations that you can make out of those vectors, right? And what are the linear combinations? I put that on the next line. That's just these expressions right here, guys. C1 times V1 plus C2 times V2 plus C3 times V3. Just all possible ways of combining your vectors together using the vector space operations. Yeah, remember in a vector space, I have two operations. They are addition and scalar multiplication. So if I use those operations to build expressions that are as general as possible, I would be writing down all of these expressions. And I'm going to take all of those and throw them into this thing called the span. And that's the idea. And I'm going to be guaranteed that I have a subspace after I do that. It's pretty sweet, pretty sweet. So we can make subspaces by the bazillions because we just grab another handful of vectors and form their span. That'll be a subspace. Then take a different handful of vectors, form their span. That'll be a different subspace. We can just do this forever, right? So let's just practice that. Let's just practice that. Let's do this warm-up problem. What is the span of these three vectors right here? So this would be V1, V2, and V3. These are 3 by 3 matrices. So that's the universe that this example is sort of sitting as a part of. It's this universe of M3 of R, but I'm taking this span. The first thing I need to know before I even take a breath is that this span, it will be a subspace of M3 of R, right? I know that before I even solve the problem. This is a subspace of M3 of R. That's guaranteed. That's guaranteed for sure. Okay, but what actually is it? I'd like to show you that. So for the solution, I'll put that over here, I think. What actually is this subspace consisting of the span of these three matrices? Well, it's the set of all possible linear combinations of those three vectors, right? So what is it? Well, I'm going to call it S if you don't mind. And it is simply the set of, well, I've got the linear combination notation right here. C1 times the first matrix. So C1 times 0, 0, 1. Sorry, 0, 1, 0. Negative 1, 0, 0, 0, 0, 0. And then plus C2 times 0, 0, 1, 0, 0, 0, negative 1, 0, 0. And then plus C3 times 0, 0, 0, 0, 0, 1, and 0, negative 1, 0. All of this is going to be such that C1, C2, and C3, those are just scalars in the real numbers. Those are just scalars in the real numbers. So this is the answer to what the span of those three matrices is. However, I would like to rewrite it a little nicer. What I'm going to do is kind of clean it up slightly. You can maybe imagine how I might be able to do that. I'm just going to put the C1, I'm going to scalar multiply the C1 inside. Same thing with the C2, same thing with the C3. I'm going to make it into a single matrix by adding everything up. So it would actually end up looking like this, guys. 0, C1, C2, right? And then on the second row, negative C1, and then 0 and C3. And then on the third row, I have negative C2, negative C3, and 0. Are you guys seeing that? If I throw the C1 in here, then it becomes, C1 and negative C1. And then when I throw the C2 in here, I get C2 and negative C2. And if I then add everything together, this is what I'm going to end up with. You guys all see that? Right, and then this is still such that C1, C2, and C3, these are real numbers right here, yeah? And now my question for you is, does anybody recognize what those matrices are? Skew symmetric matrices, you remember that? Right? The skew symmetric matrices from chapter 2, these are the matrices that have zeros on the main diagonal. Above the main diagonal, I can have any numbers that I want, but then the numbers that reflect across that main diagonal have to be the negatives of the numbers that were in the upper left, upper right corner. So guys, this is, if I want to put it into words, this is just the set of 3 by 3 skew symmetric matrices. That is what you actually have there. So I don't know if everybody remembers the group work that we did on Tuesday, but one of the problems on Tuesday's group work, I'm just going to refer to it again here. See group work number 6, and it was actually part B. You might remember on those group work problems, I was asking you to show whether or not the S was a subspace of V. And part B of numbers on that group work number 6, part B was the 3 by 3 skew symmetric matrices. Now, what everybody was doing in the group work on Tuesday was they were doing exactly what they were supposed to be doing, which is they checked that it was a subspace by verifying closure under addition and scalar multiplication. You remember that? So you had, A transpose equals negative A, and B transpose equals negative B. Right, and then we added them together and we got A plus B, and we said, well, is that still skew symmetric? Well, we have to transpose it and do a bunch of work and see if it comes out to the negative of what we started with. And it all checked out. And so we wrote A plus B as an element of S and put our little check mark there. So we did that on Tuesday. And then we did a similar thing here. And that was totally fine. And that was totally correct. What I want to show you now, though, guys, is I have another way of doing that problem. If I want to show that the skew symmetric matrices are a subspace, what I can do is I can recognize that they are actually the span of something. And anytime you take the span of anything, it has to be a subspace, no questions asked. Right? So this is just another way of doing the problem, a very different way. Checking the closure under addition and scalar multiplication doesn't look anything like trying to express my set as a span, but I can certainly do that. There was another one on the group work for Tuesday that a lot of people maybe didn't get to. I think it was group work number 6, part E. And what they gave you on that problem, I'll use this as another example. I think they gave you the set S as being the set of ax squared plus bx plus b minus a, such that a and b are in the real numbers. So I don't know if everybody got to this problem last time, but the question was, does this form a subspace? And you can do it the old-fashioned way by, checking that it's closed. It is a subspace. This is a subspace. By the way, whenever we say subspace, we should always say subspace of what? There should be a universe that this is inside of. I don't just want to say it's a subspace. It's a subspace of, if I look at the form of these vectors, they certainly look like quadratic polynomials to me, which the notation for that would be P2 of R. So I would expect it to be a subspace of that universe of P2 of R. But I can now give you another way of understanding why it's a subspace. We can check that it's closed under addition and scalar multiplication. That will work. And in fact, that's the way I would have solved it in the solutions, because this group work was sort of before this new idea of forming a spanning set. But I bet you that I can write this polynomial, or this general form of a polynomial, as a span of something. Just like this 3 by, imagine that instead of asking you what is the span of these 3 matrices, what if I started here? And I said, is this a subspace? Can you imagine yourself maybe going backwards through the work? So you say, okay, anything of this form can be broken down like this. And once it's broken down like this, it's actually looking like linear combinations. It's actually the span of something. I can do that here too, guys. I can take this set and I can basically, what I'm going to do here, guys, is I'm going to bust out the variables. We're going to get used to this idea a lot. I'm going to bust out the variables. What are my variables here? They are A and B. If I bust out the A, I'm going to factor it out of everywhere that I see it. There's an A with an x squared here. And there's also a minus A right here. So that becomes a -1. So A gets multiplied by the quantity of x squared minus 1. And then I also can bust out my other variable is the B. And when I bust out the B, I get an x and then a +1. This is purely algebra, what I've just done right here. What I have just done, guys, in going from here to here is just algebra. I just took this expression and I factored out the A and the B from wherever I could. You see? And now the point is, what do I have here? I have a scalar times a vector plus a scalar times a vector. And that's exactly what a linear combination is. I might not be calling them C1 and C2, but now I'm calling them A and B. Doesn't matter, it's the same thing, right? It's a constant times a vector plus a constant times a vector. This would be your V1 and this would be your V2. Those are your 2 vectors in this vector space. So my friends, S is equal to the span of x squared minus 1, comma, x plus 1. So there you have it. There you have it. And as soon as I see that, as soon as I see that S is a span of something, then ta-da, this always forms a subspace of V. It's basically a done deal. It has to be a subspace. In this case, the vector space is P2 of R, and we have a subspace of it. It's just those polynomials that have this form. Yes.
So from what I'm understanding, is the span just another way to find the subspace of V?
Yeah, we're making subspaces by taking spans of any handful of vectors that we want.
So what we learned on Tuesday is like one way, and then this is just
It's
another.
kind of another way.
Okay.
Yeah, it's kind of another way. But this way, what we're talking about today, guys, is something that allows us to make tons of vector spaces. Because anytime you take the span of anything, right, it will be a subspace of P2 of R. So this is a vector space in its own right. Within the larger universe of P2 of R. That's the point. It'll be closed under addition, it'll be closed under scalar multiplication. Which is really all that it has to be in order to be a subspace. Yeah, Tristan?
So are there an infinite amount of subspaces in a vector space? And are there any cases where there's a limited amount?
The only case you'd have really no subspaces is if your vector space was completely trivial to begin with and only had one vector in it, and then there would be no way to really do much with that. But I think I mentioned this on Tuesday, just to give you a really quick answer. If we take just R2. So his question was, are there going to be infinitely many subspaces to R2? I think on Tuesday, I gave you the example of a line. I think it was the line that was passing through the point 1, 2, and that line was a subspace. But you could imagine how many lines there are that are like that. I could have just as well done this line, or maybe this line, or this line, or this line. There's billions of them, right? There's actually going to be infinitely many subspaces of R2. And similarly, there will be infinitely many subspaces of P2 of R as well. Absolutely, it is an absolute free-for-all. There are billions of these things everywhere. Absolutely. Let's do another example. Kind of like a similar example to the warm-up there, guys. So what is the span? What is the span of x cubed, x squared, x, and 1? X cubed, x squared, x, and 1. Again, before I even take a breath, I already know it's a subspace. Because the span of anything is always a subspace. Have I said that at least 10 times already? My guess is it's probably going to be pretty important. The span of anything is always a subspace. So this is a subspace of what? We look at our vectors, and what kind of vectors do these look like? Like what universe do they live in? R4, I would argue R4 does not consist of polynomials. These are actually polynomials, right? P3. P3. This is P3 of R because my polynomials have degree 3 or less, right? So it's going to be a subspace. So even before I take a breath, I know that this is a subspace of P3 of R. So I haven't even solved the problem yet, but I at least know that what I'm looking at here is going to be a subspace of P3 of R. Well, let's see what it is. Okay, so for the solution then, again, I guess I'll just call it S for the subspace here. What it is it's a set of all possible linear combinations of those 4 vectors. So that would be, the set of C1 times x cubed plus C2 times x squared plus C3 times x plus C4 times 1, which I don't need to write down. And I'll just say such that C sub I is an element of R. That's what S is. And strictly speaking, we've already answered the question. Like, what is the span of these vectors? Well, yeah, so let's solve this. But I'm wondering, kind of like here, we noticed that the vectors we ended up with were the skew symmetric matrices. I'm wondering, can we describe what we have here? These are what kind of creatures? These are all cubic polynomials with any possible coefficients of any terms that I want, right? Would you guys agree that that literally actually is the entire P3 of R? It's actually the entire vector space. This might as well be ax cubed plus bx squared plus cx plus d. It literally looks like the form of a general polynomial in P3 of R. It's the entire space. So I could view this as a good news or bad news. The bad news of it is, well, I thought we were trying to create interesting subspaces, right? I thought we were trying to create stuff we didn't already have. This is a vector space we knew about since the video you watched, right? And it turns out that I haven't really discovered anything new here. I've just taken a handful of vectors, and this time when I took that handful and formed all possible linear combinations, I just produced the entire vector space. I didn't get something interesting like I did here, where I got the skew symmetric matrices. So yeah, we can get a boring answer. We can take a set of vectors and form their span and produce something that we've known about previously. That can happen. But there's actually a little bit of good news with it as well. The positive spin that I would like to put on this is that what this shows is that every single vector in P3 of R, this is a big vector space, right? Every single vector in that vector space can be built out of just 4. Just those 4 vectors are good enough to build any cubic polynomial, which means it's actually not so unwieldy after all. It's not so hard to get our hands on this vector space after all. The entire vector space is built out of these 4 specific vectors. It's kind of obvious when you think about it, but we're using this vector space terminology to describe it now. So there is a name for what's happened here, which is that when your vectors create the entire vector space out of that span, we're going to call them a spanning set. A spanning set. So I need to put a definition on the board for you here. And let's do it right here. So I'll just put the definition here for the moment. Add another thing to our notes. This is an important one, guys. This is an important one. It's important enough that I want to make sure that I get this right. So if the span, excuse me, if the span of the vectors v1, v2, and so on, up to Vn, if that is equal to the entire vector space V, like it is in that example, it's equal to the whole P3 of R. If that happens, we call that set V1, V2, and so on up to Vn. We call that set of vectors that we happen to be working with a spanning set. A spanning set for that vector space. If the span of my list of vectors is the entire universe, then we're going to call that a spanning set for V. And also we say, I'll add this also, we say that those vectors, V1, V2, and ... up to Vn, that set of vectors spans V. It spans V in that case. So it would span V. Okay. So hopefully I'm making some sense so far. Are there any questions so far here? Hopefully I'm making some sense. I'm trying. This motivates 2 questions. I'm going to ask 2 questions now. We're going to spend the next few minutes talking about these 2 questions. There are 2 questions that are related to spanning sets that everybody in Math 250B has to be able to answer or work on for any example. Okay, 2 questions that are right on the top of my mind. So the first one is, given a vector space V. Given a vector space V, how can we find a spanning set for V? Now, I just want to make it clear, why would we care about this? Like, why do we want to find a spanning set for V? Well, I've tried to give you a bit of a glimpse into that right here. P3 of R is this big, huge vector space, right? But as I just explained, everything in this big, huge vector space can be built out of just these four vectors here. And so if you kind of understand that and you recognize that these four vectors are capable of spanning every cubic polynomial, that's kind of making this vector space more understandable to us, right? Everything in this vector space can be expressed in terms of just these four, right? That's actually pretty cool. So it's like the DNA of the vector space, right? If you can figure out the spanning set, then you know how to build everything in that vector space out of those basic structures, right? It's like the atoms of the molecule. It's like the fundamental building blocks of the structure. So if we can find a spanning set for V, we're going to have that. That just helps us understand how this vector space works tremendously well. So I think that's a really good question that we want to answer. But let's ask a second question, then we'll come back and answer both of them. I'm going to answer both of these. Sometimes, for the second question, we will be given a set of vectors already. Maybe V1, V2, and ... up to Vn. Given a set in some vector space V. So if we're given a set of vectors in V, how can we decide? How can we decide, and this is yes or no, decide yes or no if they form a spanning set for V? So that's the second thing we want to talk about, is if I give you some vectors, like right here, here's an example. If I gave you these two vectors, if I handed you these two vectors, are they a spanning set for P2 of R? That would be a question, right? Yes or no. So we want to be able to answer things like that. Do we actually have a spanning set in our hands? Okay, so let's work on these two questions. The first one, thank you. The first one is actually very procedure driven. Like I can give you a cookbook process for it. How do you find a spanning set for V? I'm going to give you a 3-step process for this. Okay, so let's write down 3 steps. I guess I'll label them with A, B, and C. And the first step is really very important, which is step A, is to write the general form. Write the general form for a vector in V using variables. So you have to think about what vectors you're being asked about, and you have to write down the general form of those vectors. If it's the skew symmetric matrices, what you would be doing is you would be writing down something like this. If I want to write down the general form of a skew symmetric 3x3 matrix, you'd write this down. That would be step 1. Okay. Whatever the form is for your vectors. Sometimes step 1 will be done for you, such as right here. In this problem, the set was provided already with the form of these polynomials given to you at the start of the problem. But in general, we have to write down the form of the vector, and we're going to practice this. We'll practice this, okay? The second step is something I alluded to a few minutes ago, which is I need to bust out those variables. Bust out the variables. Sometimes I see people on their homeworks, they write out BOTV, and I usually know what that means. Bust out the variables. So you're just gonna bust it apart. You're just gonna bust it apart, which is actually what I did right here. See, I even foreshadowed my second step. I busted out the A and the B from the general form. This would be step one right here, or step A, I should say. This would be step B right here in the process that I'm describing. And then what is step C? Step C is to make a list. This is the last step. Make a list of vectors left behind. And that's actually what you have at the bottom here. You have a list of the vectors, right? So you've kind of listed them down here at the end. Okay. So these two polynomials, my friends, these two polynomials would be a spanning set for this. I know I'm calling it S here, but it's really the same as the V. Remember, subspaces and vector spaces are the same thing. So this is really your V. This is your vector space for this group work example. And here are the two vectors that will span it. You have found your spanning set. Okay, let's try a couple of examples of this, okay? I want to, before I get, I'm not going to do question 2 till after we take a break. I want to get question 1 solid first. So question 1 is, how do we find a spanning set for V? I've got a 3-step process laid out for you here. And I'm going to do the following problem. Let's let V equal the null space of 1, 2, 3, 4, and 5, 6, 7, 8. And what I would like to do is find a spanning set for V. I'm going to do an example here. By the way, this problem number 28 that is on the board, I'm probably not going to actually do it because I'm doing this one. This is basically problem 26. I think it's in the same section. So what I'm doing right now is exactly how you do problem 28 from the homework. What you're going to do here is try to take the null space of this matrix. Let me just remind you that this null space is a subspace of R. Remember which number it is? This is a 2 by 4 matrix. So the subspace is subspace of what?
R4.
Of R4, exactly. So the n value is 4. So this is a subspace of R4, right? So here we have m equals 2, n equals 4. And the null space is always a subspace of Rn, which in this case is 4. So R4. Okay. So let's go through the process of finding a spanning set for this vector space. Okay, so for the solution now, start right here. What we actually need to do before we can find a spanning set for the null space is we have to find out what is the null space. I know it lives in this universe, but what is it? Like which vectors in R4 are the null space going to be made out of? So what I have to do is kind of, so this is step A of I have my 3-step process. I'm going to label my steps here for you, right? So what I'm going to do in step A is I'm going to take my matrix here, guys, and I'm going to, remember for the null space, you're solving a system. And what do I put on the right side of the bar for my null space calculation? All zeros, exactly. So for null spaces, we're just augmenting those matrices with zeros. This is all just coming from my video that I hope you watched last week. This is basically augmenting with zeros on the right-hand side. And I just have to do some EROs here. I'm actually going to do some EROs. So I have to leave the first row the same. Oh, by the way, I should mention, there are unknowns associated with these columns. I don't care what you call them. You can call them X, Y, Z, and W, or you could call them A, B, C, and D. It really doesn't matter. I think I'll go ahead and use X, Y, Z, and W. So kind of harkening back to chapter 2, when we were solving systems of equations, we hopefully remember that the columns are lined up with these unknowns. Okay, now if I take, what is it gonna be, A12 of -5. So I look at this 1 and this 5, I wanna turn that 5 into a 0. To make that happen, I'm gonna take -5 times the first row and add it to the second row. That should give me 0, -4, -8, and -12. And then, of course, 0 again. And then finally, I'm going to multiply row 2 by -1/4. And so now the first row is still the same, but the second row will be 0, 1, 2, 3, like so. And now we have the row echelon form that we need, right? To be able to solve this thing by back substitution. I'm still on step A. I'm still on step A, right? I'm still trying to figure out what is the general form of a vector that's in this null space? What does it look like? Okay, so, well, I've got to do my usual thing. Z and W are both free. So Z is R, W is T. These are both free variables, right? Those are the unpivoted columns. The third and fourth columns are unpivoted. Thank you, Reed. I want to solve what Y is. I can see from the bottom equation that Y plus 2Z plus 3W should equal 0. That's the second row of my system here. And so if I solve this for Y, I'm gonna get, if I move everything to the other side of the equal sign, I'll get -2R minus 3T for Y. Okay. And then I also have to solve for X, and I can do that using the first equation. So X plus 2Y plus 3Z plus 4W, that also has to equal 0. And if I now solve for X, I'm going to move everything to the other side. So -2 times Y, I'm going to replace what Y is. -2 times Y minus 3Z, which is really 3R, and minus 4W, which is really 4T. And if I clean this up a little bit, just to make it look a little nicer, I should have R plus 2T. Just check my notes, make sure I'm not messing this up. Yeah, that looks like what I have. So X would be equal to R plus 2T. Good enough? And now I've done something here that I have not done the best job of ever of writing this up, because I like to organize this a little better. X should come first, then Y, then Z, and then W. When I write down my null space of A, when I write it out what it is, I should be writing out the X first, then the Y, then the Z, and then the W. So the R plus 2T would go first. And then the Y variable, which is -2R minus 3T, that would go second. The third one is Z, which is just R, and the fourth one is W, which is just T. And this is such that R and T are in the real numbers. So this is just a crash course review on Gaussian elimination. We did this 2 chapters ago. We would have been able to do something like that. All of this in blue, all of this in my blue marker is still just step A of the process. Write down the general form of a vector in V. Well, here it is. This is step A. There's 4 slots. That's expected. It's a subspace of R4. So I would expect 4 slots. And the form of those vectors is now expressed using variables, in this case, the R and the T. Any questions so far? Actually, for that homework problem from section 4.3, they only want you to go this far. Because after all, section 4.3 is not about spanning sets. That's next week's homework. for the homework you're doing for tomorrow, you would basically do this process with whatever the matrix was that they gave you, and then that's your answer. Okay, but we're gonna take it a step further now. We're gonna take it a step further. I'm gonna go on to step B. And step B says bust out the variables. That just means factor them out. I've got two variables here to factor out, so I'm gonna factor them out right on the very next line. I have to factor out or bust out the R. When I take the R out, so here's what you have to do, guys. You look at all four slots and you take out as whatever the multiples of R would be. So in the first slot, there's just one R there. In the second slot, there's -2 R's there. In the third slot, there's one R. And then in the last slot, there are no R's anywhere, so that would have a 0 on it. Okay, so what I have here, guys, is I have pulled out the R from every single slot. Okay, and then plus, and I do the same thing with T. So T, I pull out the 2 from the first slot, -3 from the second slot, no T's in the third slot, and 1 T in the last slot. So I'm just busting it out. I'm trying to figure out the building blocks of my null space right now. What are the basic building blocks of this null space? And this is gonna help me to do that. Once it's busted out, I go to step C. Step C just says, make a list of the vectors that are left behind. When you look at this linear combination here, the vectors that are left behind are just these two vectors right here. So my answer is, I make it, you should use squiggly braces still and make a set out of this. 1, -2, 1, and 0, comma, 2, -3, 0, and 1. And that, my friends, is your final answer, right? Find a spanning set for the null space of that matrix. Here it is. The only part of this that's new is these last two lines. Everything else you see in this blue writing is stuff we did in chapter 2. So this is actually mostly review of Gaussian elimination. But this null space, which sits as a subspace of R4, seems like some mysterious thing. I don't know how to describe it really, but actually it's not so mysterious after all. It's just built out of these two vectors. Everything in the null space can be made as a combination of these two vectors. That's the end of the story of that. It's actually quite straightforward. Everybody okay? Questions? Go ahead, Oscar.
Why don't the numbers in the null space have to also exist within R4?
The numbers in the null space exist in R4. R4 is vectors with 4 slots, right? So individual numbers are gonna make up those slots, but the numbers themselves are not the vectors, right? The vectors have to have, commas separating the 4 numbers, because that's how the vectors in R4 look. I don't know if I'm answering your question. Is that reasonable?
Yeah, it's
It's a good question, because getting the right notation and understanding the notation for these things is actually one of the challenges I find. So, yeah, I like that. Yeah, Reed?
Can you prove that C makes up, you know what I mean? Like
The spanning set?
go backwards with it?
I could have asked you, what is the span of these two vectors? That would be going backwards. What is the span of them? And then you would have written this down. And then on the earlier example, I was able to look at it and say, oh, that was the 3x3 skew symmetric matrices. Or, oh, that was P3 of R. If you look at this, or even this, right? If you come into my office and ask me, what is this? I'm gonna be like, well, it is what it is. I don't know what else to say, right? It's a set of vectors in R4. It doesn't have the sort of easy description unless you knew this matrix ahead of time, right? Unless this was in front. You're saying if I only had these two vectors, I mean, I can take the span of these two vectors and I know it'll be a subspace of R4. But what subspace is it? Well, it's this. It's as good as I can describe it, okay, if I don't have the matrix in front of me to begin with. Yeah. Usually we're gonna be going this way with it. I'm gonna be giving you the subspace and asking you to find a spanning set for it. That's generally what these questions are gonna look like. Let's practice one more of them. Let's do one more, and then we'll take a little break. So one more practice example. So let's come here, I'm gonna do one more example. Find a spanning set. For B equals the set of P of X in P3 of R such that P of 5 is equal to 0. So let's just be careful here. I'm not asking you for a spanning set for P3 of R. If I wanted that, we could write down the answer already, because we did it earlier. This would have been a spanning set for P3 of R, but that's not my vector space. My vector space is those polynomials in P3 of R such that, this is the important part, such that when I plug in 5 for X, I get 0. That's what it is. So it's not all cubic polynomials that I'm looking at here. It's only those cubic polynomials that happen to cross the x-axis when you plug in 5 for X. In other words, 5 is a root. So that means that doing step A is going to be a little bit more involved than you might think. Step A is where I have to write down the form of my vectors. Now, normally I might be thinking, well, if it's a cubic polynomial, can't I write P of X as ax cubed plus bx squared plus cx plus d? And that's absolutely fine. But if I stop now and I say that's my form, I have not incorporated the condition that P of 5 has to be equal to 0. So I'm going to do that. I'm going to refine this notation to include this assumption here, that P of 5 is 0. How do I do that? Well, if I just plug 5 in, for X, what will I get here? 125A plus 25B plus 5C plus D, and we're setting that equal to 0. And this is actually going to put a constraint on the values of A, B, C, and D. They can't just be any old random numbers. They actually have to make this equation work. And in fact, you can think of it, if you want to, we don't really need to do this because it's such a small example, but we can think of this as a small little mini system of equations to solve, although there's only one equation. Okay. So it will look something like that, and this is your A variable, this is your B, this is your C, and this is your D. So we can think of it that way. Here's your pivot, right? Basically the pivot position is going to be there. And what you see is that B, C, and D are all pretty much going to end up being free variables. And the only variable that you really have to deal with as a pivoted variable is A. And I can solve for A. Right, so I can solve for A. Let me throw everything to the other side of the equation, right? I'm going to solve for A by moving everything to the other side. That means I need to subtract those terms over and divide by 125. I'm going to do that all in one step, if you don't mind. 25 over 125 is 1/5, so it'll be negative 1/5 of B. And then if I move the 5C over and divide by 125, I'll get minus 1 over 25 times C, and then minus 1 over 125 times D. So if I've solved for A correctly, that should be what A is. Right? So if you believe that, if you're good with that, now I can give you the correct form for P of X. This is not it. This is not it because it doesn't incorporate the requirement that P of 5 is 0. But now, if I replace A by this, I'll get the correct form. Let's write it down. So P of X is equal to, the A variable is first, so -1/5 of B minus 1/25 of C minus 1/125 of D, that's all times x cubed. And then plus bx squared plus cx plus d. And that is step A. We have now finished step A. Isn't this is so different than what we did on the previous example? This is why I have to first show you an example involving vectors in Rn. Then I gotta do another one to show you how it looks for polynomials, right? We have to go through lots of examples to kind of get the hang of this. But this is the form for my polynomials that are in V. With me? Now, let's go to step B, bust out the variables. By the way, when we're working with polynomials, guys, the x is not considered the variable. That's part of the object itself. That's part of the vector itself. It's a piece of that notation. The variables are the b, the c, and the d. Let's bust them out. So step B, I'm going to write p of x as, so if I bust out the b, first of all, if I bust out the b, I'm going to get -1/5 of x cubed, and then plus x squared. So all I'm doing is I'm scanning this thing from left to right. Where are the b's? So I've got a b right here that has a -1/5 in it, but there's also x cubed. And then there's a b right here with an x squared in it. There's no other b's, so that's the end of the first part. Right? Now I'm going to do the same thing with c. So I take c, I bust out the c from everywhere that I see a c. There's a -1/25 with an x cubed right here. And then this c has a plus x on it. Okay, and then finally I have d, running out of room here, but I'm going to squeeze it in. The d variable has a -1/125 x cubed plus 1. Plus a 1, because the d at the end here, when I factor that out of the last term, there's just 1 left behind. Okay, that's step 2. And now step 3, my friends, is simply to make my list. Make a list of the vectors. What are they? They're going to be this guy, and this guy. We're just going to make that list now, guys. So step C is our final answer. The set of -1/5 x cubed plus x squared, comma, -1/25 x cubed plus x, comma, -1/125 x cubed plus 1. And we just list those vectors out in a set. We don't even really have to think about it too hard. We just make that list. By the way, guys, if you plug 5 in for x on any of these polynomials, you will get 0. That's part of what was the deal that we were trying to set up, was we were looking for polynomials that when you plug in 5, you get 0, right? How many vectors did I end up with here, by the way? 3, right? How many vectors did if I was doing the P3 of R, which is the big universe that we started with, right? Remember we did this one earlier. How many vectors did we need here? 4. That makes sense to me, because after all, this is a subspace of P3 of R. So however big P3 of R is, the subspace, which is inside of it, should be smaller. I'm not surprised that it only takes me 3 vectors. They might not be as nice of vectors, but it's less vectors to span this subspace than it was for the whole big universe of P3 of R. We're going to talk more about that next week, this idea of the size of a vector space. But you can kind of get the feeling for it. The more vectors that you need to be able to span your subspace, the bigger that subspace is, sort of in some kind of a size sense. So, yeah. So anyway, gosh, I really think we've hit this question pretty good. 3 steps to finding a spanning set for a vector space. You are finding the building blocks. You're finding the basically the fundamental core of what the vectors are made out of in that subspace. This is not like some small passing Like mathematicians do this all the time. Let's find a spanning set for a collection of vectors. So this is not a minor thing that we've learned how to do right now. I'm good if you are. Are there any questions about anything here on like either of these examples here? Okay about that? Okay, we still have that second question, which is if I give you some vectors ahead of time, it's a thumbs up, thumbs down. Will they form a spanning set or not? Because sometimes we get handed some vectors and we're asked about those. We'll take that on after we have a little break. Let's take 10 minutes, and if you want to add anything else to my board over here, you can, but otherwise let's take 10 minutes and stretch your legs. Oscar, what is your last name again? Oh, then this is yours. Yeah.
It's like, well, look at your, it's on Twitter. You like, look at Twitter. Wait, which one are we adding?
And maybe the true rules. Oh, let's take that. Oh, wait. See. Okay. Oh, it's got a big different one. PVC. Yeah, I do. I think he says a different schedule, so it's in there. Someone was getting invited to it. Halloween party. No saying that. I think the third, yeah, you're invited. The third, like the Thursday? No, oh, you know that it's the Thursday. Maybe the 31st. Be fire. Oh, the Allen. Yeah. Would be fire. It would be sexy soon. I don't want to know. You should see this awesome. This shit's ridiculous. I already showed you Allen. Yeah, you did. Yeah, we went to the guy. That shit's fine. Yeah, it's fine. It's like what was it? What's more? There's so much of everything.
Can you tell me which parts those would be? On the true false, because I don't remember which parts.
I got A and B.
Of 4.2.
4.2.
Got
Yeah.
it, got it, got it.
We like have the answers, we just want the right explanation.
Got it, okay.
I think the true and false are pretty important. So like.
Conceptually.
Conceptually to
Yeah.
understand.
They really are, they really are.
Someone's circle to healing. Oh, healing. Wait, I can't read that part. Needs. Oh. Get a grip. Vaguely, but. That shit was. I used to. There were kids like. It was basically like shooting. But as a people, they would shoot each other. It was just like, yeah, bro. It was so intense. Probably. 16 months. Also, only have 24 seats, 1 point screwed. One question. It's game over. Yeah. Grade still went down. That's crazy. Average one thing. He's still. Just this is what we were here. You were a burrito. Oh, right. Dude, I want to be. You totally could do it. But like, then should also just have to like make no money. So like, just like pull up realtors and let's just try it. Probably did that 1 year. So something. It's like borderline. Confidence. Good from. Yourself.
Oh,
Not being good. I was
did
thinking
not
that
assign you 4.2 A and B.
you didn't. True fall.
4.1.
Oh, was it 4.1?
It's 4.1.
Oh, it's 4.1? Oh, I forgot to write 4.1. So you meant 4.1?
Yeah.
Oh, okay. Let me see what that's about.
Oops.
It's okay. I was just getting myself confused. Oh, yeah. Mhm.
Particularly the.
So this is just X, Y. This is the one you're talking about?
Yeah, more so the second one.
And the second one, which,
I guess one.
second one was every. X, Y, Z in Article 3 has unique inverse. Exactly one. Yeah. We'll talk about it.
What's up, YouTube? Welcome back to another Scott Annan linear algebra lesson. Inverse. 'Cause that's what that's adjacent. Oh, yeah. Oh, you do? No, she not. That's good. She's so much. No, I wouldn't. No, I guess. I wouldn't.
Anybody got any big plans for the weekend? Sleep, probably. I'm gonna try to go hiking
Wingstop.
up in the mountains, but it's supposed to snow today. So let's see, that'd
It's
be
so
kind of interesting.
I said Wingstop.
Wingstop?
And you go hiking.
I'm gonna go hiking.
Do you have like hikes that you just like do regularly? Like you have like a.
I try to do different stuff all the time. I try not to repeat myself.
You should just
You know,
skydive.
like a go-to hike.
I don't know if I don't like that idea very much.
Really?
I'll watch you do it.
I'll skydive. I kind of want to.
You've done the- you've done the-
Huh? I have done that. What's that?
I want to skydive.
No, last weekend I was great.
No.
This weekend, I'm gonna hopefully not be stuck in my office.
Who's missing this for that?
All right, guys, I think there's several problems from the homework that are on the side board over here. So I'd like to chat with you about them briefly to help you out. And maybe even add one more of my own to that list, if that's okay. I'm trying to make this assignment for tomorrow a little nicer for you. I would have just taken off more problems, but I went through. You guys have all seen where there's the recommended problems. Those used to be, I wanted to require all of them. And then I finally talked myself off of a few of them, but I was like, I can't take off these other ones because there's something to be learned from each of them. So I really think they're important. If I'm asking you to do them, it's because I think they're important. So let's try a couple of them. In the section 4.1, I guess it is, there's a couple of true false items. This is right near the beginning of the assignment. And they just ask you, is the vector xy the same as the vector xy0? Now, the first vector lives in R2, whereas the second vector lives in R3. They're not even in the same universes. It would be like saying that a matrix is the same as a polynomial, or that a physics vector is the same as a calculus function. You would never say that, right? You would never say that a vector in one universe is equal or the same as a vector in another universe. So this is false. This part A here would be false. And remember, I like to have a justification provided. You can make it very brief. I would just say something like the vectors belong to different vector spaces. They do not live in the same universe. So you could just say that as a very brief little reason. R2 is not the same as R3. They aren't even really subspaces of each other, right? They're just different objects altogether. They really are not comparable. If they're not comparable, then we don't want to say that they're the same. Okay, so that's a false one. The second part, though, every vector has a unique additive inverse. That is true. And what I could do to justify that is I could just say what that additive inverse is, because there is only one thing it can be. Remember, the inverse, I talked about this briefly when I was discussing the axioms. The inverse of a vector is just whatever you have to add to it in order to get back to the zero vector. Right? Inverses cancel each other out, right? And here we're talking about under addition. So you could just write down what it would take. What would be the additive inverse of XYZ? What would you have to add to XYZ in order to get 0, 0, 0?
Negative.
Negative X, negative Y, and negative Z, exactly. That would be the whole answer. You just have to put negatives in front of all of those vectors, and that's the only answer. So it's a unique inverse for XYZ. So in a vector space, the axiom that's in that list of axioms just says there exists an additive inverse for every vector. But this is saying a little more than that. It's actually saying that not only does it exist, there's only one. There's a unique additive inverse for every vector. Okay, great. Let me help you with a few of these other problems. First of all, 4.2 number 1 is actually in the video notes. I did it as an example. It's the one about the rational numbers. So if you go digging into your notes, I wrote that all the way out in detail, so I'm not gonna repeat myself on that one. 4.2, let's see what else we have here. Yes, number 3 from 4.2 is this problem here. S is the set of matrices, I think they're n by n matrices. Such that, so A is a n by n matrix such that A is upper or lower triangular. And they're asking you whether or not that forms a subspace, right? No, sorry, they're just asking, is it closed under addition and is it closed under scalar multiplication? If you want to make your life easy here, guys, if I rewrite this book again, I'm probably just going to make n equal to 2, just to make it simpler. So we can assume that these matrices are just 2 by 2 matrices. And they're just asking whether it's closed under addition and whether it's closed under scalar multiplication. If I start with the addition, would it be true that if I take a matrix that's triangular and add it to another matrix that's triangular, that the result would be triangular?
No.
It's either yes or no. If it's no, you can give me an example. So you could give me, you know, specific 2 by 2 matrices that kind of show the point. Right? Somebody want to throw out a triangular matrix for A for me, Adrian?
For triangular, it's just 1, 1, 1, 0.
1, 1, how about 0?
1, 0, yeah, 0.
Yeah. Yeah, exactly. So that would be upper triangular. That looks good. So that's in S, right? We always like to point out that it belongs to S. Can somebody give me another triangular matrix that I might want to try to add to that?
1, 0, 1, 1.
1, 0, 1, 1. Now that is also triangular. It happens to be that the first one is upper triangular and the second one is lower triangular, but they're both in S because this says or, right? A could be upper or lower triangular. And then, well, what happens when you add them together? Well, you get 2, 1, 1, 2. And is that triangular?
No.
Not at all. There's no zeros in it, right? This is not an S. So this fails. It fails to be closed under addition. So by the way, that tells you right now that this will not be a subspace. Normally, we would just say at this point that this is game over. As soon as this axiom fails, there's no point in thinking about it anymore. There's not going to be a subspace here because this axiom fails. The instructions in this little section of the assignment, though, they actually do ask you, would it be true that it's closed under both of these operations? So for the scalar multiplication part, normally we wouldn't even do this because we would have already said that it fails to be a subspace. But if I wanted to know if this was upper or lower, if this was closed under scalar multiplication, I could think about it here. Let me give myself a little bit more room to write this up. What do you think? Do you think if you start with a triangular matrix and you scalar multiply it by a number, that you'll get a triangular matrix again?
Yeah.
Seems reasonable. You have to think about it. If notice I haven't written anything down yet, I'm just thinking about it. If I have something that's triangular and I throw a scalar through it, that shouldn't change where the zeros are, should it? Shouldn't, right? So I think this one probably is true. Now, if it is true, I'm not just going to make a specific example. Specific examples are great when things fail, because you only need one example to show that it fails. But when it's true, here what you need to do is you need to say more generally that you're going to take A to be an element of S. And then we have sort of two cases. So case 1 would be that A is upper triangular. So for upper triangular, you need to leave it very general now. So something like A and B on the first row, and then 0 and C on the second row. I forgot. I should also let K be a real number here at the beginning of this. I usually like to use K for my scalar. And then I'm just going to check, well, what happens when I take K times A? Well, the K just gets multiplied into the slots of my matrix, and I just take a breath, I look at that, I say, well, is that still triangular? And the answer is yes, because the 0 is in the lower right corner, lower left corner, so it is in S, yeah. Okay, and then you have to do another case, which would be if A was lower triangular, so that might look like X, 0, Y, Z, something like that. This would be another possibility. And then again, we have another verification. If I multiply that through by K, I'll get KX, 0, and then KY and KZ, and sure enough, that is also in S. So doesn't matter whether it was upper triangular or lower triangular, the scalar multiplication works. Preserves the triangularity, yes,
Is 0 a real number?
it sure is.
So if k is 0, wouldn't it not be true?
It would be true because 0, 0, 0, 0,
Oh, it's still.
that is triangular,
Oh.
for sure, yeah. Great, so I think we're all good on this. This one seems to work. Let's see. Number 6. Number 6, I don't really want to do this one fully because I did one almost like it on Tuesday in class. So this is one that involves a differential equation. So S is the set of y in C of minus infinity to infinity, let's say, such that, what is it, y prime plus 3y equals, what was it, 6x cubed plus 5. Well, actually, I think in class on Tuesday when I did do a differential equation, but I think I was just checking that it was a subspace and I pointed out that the 0 vector fails. And so therefore it wasn't a subspace, but this is actually asking you to check the closure under addition and scalar multiplication. Let me write it out. I'll go ahead and do this one. So for the closure under addition, by the way, the gut feeling about this one should be that this won't work. How do I know that without even thinking about it? It's because I know that the 0 vector check fails. If you take the derivative of 0 and add 3 times 0, you're not going to get 6x cubed plus 5. It's not going to work. The 0 isn't part of S. And if it fails the 0 vector check, you already know that this is not a subspace. So you know that these closures are going to be problematic. At least one of them has to be. Right? Let's check it out. What would happen, right? If I take y1 and y2 in S, if I imagine starting with that, I usually like to make a sentence out of it. So let y1 and y2 be in S. Well, so then what does that mean? That means that y1 prime plus 3y1 is equal to 6x cubed plus 5. And it also means that y2 prime plus 3y2 is equal to 6x cubed plus 5. Both of those would be true. That's what it means for those two functions to belong to my set. They have this condition, they satisfy that differential equation. But what I'm going to look at now is what about when I add them together? This is the addition that we're looking at, right? So if we take the y1 and y2 and add them, and we try to plug them in to the left side of that differential equation. So here I've got the entire y1 plus y2, that's my function. Take the derivative of it, add 3 times that entire function. I'm just really working on this, right? So I just take the derivative of the thing plus 3 times that thing. Everywhere I have a y here, now that's being played by the role of y1 plus y2. And the question is, does this equal 6x cubed plus 5? Because that's the $1,000,000 question. If you're going to be in S, that you have to make that equation work, that it should equal 6x cubed plus 5. Well, if you work this out, if you start foiling out this I did do on Tuesday. If you foil out this derivative and you regroup these terms, you can put all of the y1 parts in the front, and you can put all of the y2 parts in the back. So just rearrange the terms a little bit, put everything involving y1 in the front. And put everything involving y2 in the back. Well, I'm sorry, I'm gonna write a little bit down here on the bottom, guys. If you need to stand up in the back, go ahead. I just want to put one more line here. This first part, the y1 prime plus 3y1, that is 6x cubed plus 5. And the y2 prime plus 3y2, we already wrote down that that is 6x cubed plus 5. But if you add that up, you do not get 6x cubed plus 5 anymore. What you get now is 12x cubed plus 10. Which is not what you were supposed to get. That's the wrong thing on the right-hand side. So, y1 plus y2 is not in S. Make sure you get that slash on your element symbol there, your belongs to symbol. It is not in S. This actually fails. This closure under addition actually fails, as we see now. This is kind of how you would write that up. That look okay? Notice we're not even solving the differential equation. This would be first order linear. Solve it using an integrating factor and go through some of that stuff. We did that in chapter 1. But for the time being, we're not interested in actually solving it. We just want to figure out, is it actually closed under the operations? It's not closed under addition. This blue writing shows that it will not be closed under addition. I'm going to leave the scalar multiplication to you. That's where you have to bring in a k. And so, well, actually, let me start this. I get too excited. I can't stop myself because I like these problems. I'll at least start it. For the scalar multiplication, I have this rubber stamp way of starting it off, which is to just say, let y1 be as above. And k is usually my real number that I like to choose for the scalar multiplication. And what you're going to do is you're going to take k times y1 and stuff it into the left side of this differential equation, right? So I can't help myself. I'll just go ahead and show you. But you have to make sure you understand this. Okay, sure, you can copy it down, turn it in, the grader's going to love it, right? But in terms of your understanding, you got to make sure that you're following it and asking questions if you don't. But everywhere I had a y in my differential equation on the left side, I'm now just going to stick that k times y1 part. And I'm going to ask myself, does this become 6x cubed plus 5? What do you suppose I'm going to do with this? Factor out the k, exactly. Pull out the k, that's kind of a natural next step here. And once I've done that, I have k being multiplied by 6x cubed plus 5. And is that equal to 6x cubed plus 5? It is not. Now, you could say, well, wait a minute, what if k is equal to 1? If k is equal to 1, then this would be true. However, this has to be for all values of k. So it might work for k equal to 1, but it's not going to work for k equal to 2 or 3 or 4 or any other number. And so therefore, this also fails. Right? This also fails. I guess I should write. So k times y1 is not in S. It's not in S. So it actually fails both of the axioms. It fails them both. It's a done deal. Good enough? I see some of you taking pictures with your phones. That's totally fine. You can write, but you have to write it up later. Please do not submit my pictures that say to my grader, here's my work. I'm like, no, I think that looks like Dr. Hannon's handwriting. Anyway, oh, I put this one up here. I forgot. I kind of left this hanging. This one here, show that S is a subspace of R. Would you mind if I let you do this problem using the stuff we learned today? Technically, they're giving you these vectors in R2, and they're asking you to show that it's a subspace of R2. Normally, what we had learned previously is that you would do this by verifying that it is closed under addition and closed under scalar multiplication. However, does anybody see a fast way to show that this is a subspace? Without checking that it's closed under addition or closed under scalar multiplication. Basically, we're looking at points that look like 2k, comma, negative 3k. I'm just gonna express my set here. You see how I can just in no time at all, I can tell you that that is a subspace. Holman? Yeah, this is the form of the vector. Let's bust out the variable, right? So I'm gonna let you guys do this one the fast way, if you want to. You can do it the other way if you want and check that it's closed under the operations. But this is the fast way to get it, is just pull the k out. And then what are you looking at here? You're looking at, basically something that is all possible linear combinations of 2 comma negative 3. This is just the span of the point 2 and negative 3. And anytime you take the span of anything, it is always a subspace. So S is a subspace. Don't even have to think about it any harder than that. As soon as you realize that what was given to you is a span, then you're good to go. By the way, this would just be a line. We did one kind of like this the other day. This would just be a line that goes through the point 2, negative 3, and the origin. And so your set, I think they ask you to draw a picture of it. It's just that line. It's just that line that goes through the point 2, negative 3 right here. 2, negative 3. And you make that line through the origin, and that's your subspace. Be careful. It would be very easy for me to change the answer to this problem. Okay, you don't want to do this part. Just watch for a second. If I slip a little +1 in there, I try to play games with you and do something like that, this all of a sudden is not a subspace. You cannot bust out the k like I did in this solution because there is no k on that +1 term. So you would not be able to express this one as a span. In fact, if I wanted to argue that this one was not a subspace, I have a very easy way to do it, which is to simply point out that you do not have the 0 vector in that set anymore, right? You cannot make both slots turn into 0 and 0 at the same time. So this is now a line that has been shifted off of the origin, and that's not a subspace. So it's very easy to tweak. I did this one time. I had a test question, and it was like a 5x5 matrix. It was some huge, it looked horrible, but somewhere in one of the entries, I stuck a little +1 on the end of whatever was there. And so what everybody was supposed to do was just look at it and realize, oh, all of these numbers are fine, except there's a 1 in that one spot. I can't make the 0 vector in my set. So it's easy to play those kind of little games. I think I've gone through most of the problems that were over there. There's one other one that nobody put over there that I'd like to mention something about if I could. I'll do it real fast, and then we're gonna come back to the second question here. It's number 12, I think, in 4.3. Number 12 says that this is 4.3. So some of you might not have gotten to this one yet. It's a little bit further into the assignment, but let me just. I try to be helpful with the homework. I know I give you a lot to do, so I would like to help you with this. Let's see if I can restrain myself from just doing the whole problem. S is the 2x2 matrices whose 4 entries sum to 0. So, any matrix where the 4 numbers add up to 0 would be an S, otherwise wouldn't be. So for example, obviously the 0 vector is in there. So it's gonna pass the zero vector check. If you add up those four numbers, you definitely get zero. They're asking you if S forms a subspace of V. So again, we could do this by verifying closure under addition and scalar multiplication. But I want to give you another thought on how to do this problem, which is to use what we did today. You're welcome to do that if you would like to. If I was going to do it the way that I learned or that I explained today, what I would need to do is try to express it as a span. Because just like here, if S is the span of something, it's automatically a subspace. So I have to figure out, well, what matrices would span S? How could we get our spanning set for S? Anybody remember what we would do first? It's a three-step process that I just talked about. Go ahead, Jose.
Write the general form.
Write the general form of a vector in S. Can anybody do that for me? It's got to be a 2x2 matrix and its entries have to add up to 0. How would it look? What I sometimes like to do is I like to pretend that I wanted to just make a specific example of a vector in S. And would you agree that I can put any number here, any number here, any number here, as long as I cancel it all out with the last number? I just have to make sure that the last number cancels out what all of the others have added up to. If you kind of understand how that was done, you might not be surprised when I write down this form as any number here, any number here, any number here, but the negatives of all of them added together going here. So the four entries have to add up to 0. You have freedom to choose 3 of those 4 numbers however you want. The final number has to cancel out what you have up until that point. Okay, and now this would be such that A, B, C are elements of the real numbers. Can I get a hand check? How many people are comfortable with that form for the matrices in this example? Raise your hand. That's not a huge number of hands. Okay, so I'm not saying anything about rows and columns. It's just the 4 numbers together collectively. They have to, at the end of those 4 numbers being written down, they have to add up to 0. So instead of writing A, B, C, and D, I mean, I guess I could think of it this way. You write down any 4 numbers, but then over here you add this little condition that they have to add up to 0. If you do that, you realize that you could replace the D with negative of A plus B plus C. And then it looks like this one. A little better? So it's another way of thinking about it. So you put any numbers here, any number here, any number here, and then cancel it all out with that last number. Once you've got that form written down, now you're running with the process that Jose started reviewing. We write down the form of the vector, we bust out the variables, right? So I'm going to bust out the A. So if I bust out the A, it's going to look like that. If I bust out the B, it's going to look like that. And if I bust out the C, it's going to look like that. And what do you have here, guys, is nothing more than a linear combination of these 3 vectors. This is your V1, this is your V2, and this is your V3. Those are 3 vectors, and you're building linear combinations of them. Now that sounds like forming the span of those 3 vectors, right? This is just the span of exactly those 3 vectors. So here we have yet another example practicing what we just learned today. And this would be your spanning set, these 3 matrices. Notice that they all add up to each of these matrices, the entries add up to 0, right? And it turns out that any 2x2 matrix where the entries add up to 0 can be expressed in terms of these 3. In terms of those three. Exactly. So you could use that as your justification on number 12. It is a subspace of M2 of R because it is a span of something. That's always a valid reason. You all okay with that, Jose?
In this case, this was working backwards compared to the first example you showed us. Right. Because you gave us the span first and then you.
Yeah, on the warm up today, like 2 hours ago, yes, I had started off with a set of vectors and said, let's form the span of them. Yeah, this is working backwards, which actually this is more commonly what you do. You usually have some subspace that has a nice description and you want to figure out how you could span it using just a small number of vectors. Yeah, that's basically the idea. Okay. Well, I have some good news and I have some bad news. The good news is that I have done a lot of your homework for you. The bad news is I'm not getting as far through some of this stuff as I would like to. So I may have a little YouTube time for you this weekend as well. Adrian? I'm just labeling them here with names. You don't actually need those. Is that what you're asking?
No, like matrices.
Well, how do you get the matrices?
Yeah.
By just busting out the variables. So I see in this general form that I have A's, B's, and C's. So those are the three variables, and I see them listed here. So I have to take each of them and sort of pull them out of the matrix. When I pull that A out of the matrix, I look at, well, where were there A's in this matrix? There was one A in the upper left corner, and there was a negative A in the lower right corner, but there were no A's on the other two entries. So those are zeros with respect to busting out the A. You with me?
Yeah.
And I do the same thing for the B and then for the C, and I get the whole thing.
Can you do the same thing where you replace B with the three parameters?
So what you mean is if I had done this,
Yeah.
that is a great question. This is also a correct form for these matrices. And if you did this and busted out the A, B, and C, sorry, the A, C, and D here, you would get another correct answer. Ooh, that gets into a whole can of worms, doesn't it? There can be more than one spanning set for a vector space. That is true. So you'll get a different answer if you bust the A, C, and D out of here than if you bust the A, B, and C out of this one. Good point. Yeah, that's a really good point. Okay, I don't have a long time, but I'm gonna start on this second question here. And I'm probably gonna have you guys watch some video this weekend to catch up because I don't want to fall behind. But at least you don't have so much homework to worry about now. I've done probably half the assignment for you. At least. So what we'll do here is just get started on it, and then I'll probably have a video that I'll ask you to watch over the weekend and take some notes on for me. There was that second question from earlier. If I have a vector space in advance, well, sorry, the first question we're good to go. Given a vector space, find a spanning set for it. We've practiced that 4 or 5 times already today. That second question though, what if I give you some vectors ahead of time? Whoops, got a parenthesis here. If I give you vectors ahead of time, decide yes or no whether they form a spanning set. Okay, so here's an example. I'm going to give you these 3 vectors. They obviously have 3 slots each. And these are vectors that are in R3. And I'm just going to ask you, are they a spanning set for R3? Now, what that would mean is that, is it true that everything in R3 can be built as a combination of those 3? That's really the question. So for the solution here, what I can do is I can try. I can try to take X, Y, Z. This is just some random element of R3. I'm going to write the word try across that equal sign. I'm going to try to set it equal to a linear combination of these three vectors. So that would be C1 times 1, 1, 3 plus C2 times 2, negative 1, 4 plus C3 times 3, negative 3, 5. And I'm kind of gonna put a question mark there because we don't even know if this is possible. Notice on the left side, I have a generic vector, right? I'm not picking something specific here. I'm picking a generic vector that would be in R3, and I'm asking myself, regardless of what X, Y, and Z are, would I always be able to solve for C1, C2, and C3? By the way, I actually don't care to actually solve for C1, C2, and C3. I just want to know, can I solve for C1, C2, and C3? In other words, can we solve for C1, C2, and C3? Now, this may look like only one equation, but it's actually three equations because there is a left slot, a middle slot, and a right slot in both sides of that equal sign. So there's actually three equations there. The first one is the first one is x equals, so if I just read the left slot of each term, I'll have x equals C1 plus 2C2 plus C3, 3C3. Okay. And then, so that's if I kind of focus on the left entry of everything I see in my vector equation. And then if I go to the middle entry, I have a y on the left side, and on the right side, I have a C1, and then this is actually going to be a minus a C2 and a minus 3C3. That's the middle entry. And then the right slot is Z equals 3C1 plus 4C2 plus 5C3. So that would be the right slot. So we're just looking at the left, the middle, and the right slots, and we're making those equations. Now, this is a system of equations.
Would it be -3 for
Did
the
I screw up?
middle, for right, for the Z? For where it says plus 4 is
Z.
C2?
This should be plus. I think the right slot is 3C1, 4C2, and 5C3, all with pluses.
Oh, so you're doing each term.
So I'm focusing on, like, for the right slot, I'm picking the right entry, the right entry, the right entry, and the right entry, and I'm making an equation out of that. Yeah. Okay? Now, this is a system of equations. Remember, I don't want to actually solve it. I just want to know, can I solve it? Mathematicians are funny. We find out, yeah, I can solve that problem and go back to bed. And don't actually figure out how to solve it. This can be written as a augmented matrix. So I'm going to put a 1, a 2, and a 3, and I'm going to augment that with x. So I kind of have to switch the sides around a little bit. And then a 1, a -1, a -3, and a y. And then on the third row, a 3, a 4, and a 5, and a c. So I'm just putting it into an augmented matrix. My unknowns are C1, C2, and C3. And now I have to do enough EROs to decide whether a pivot goes into the far right column or not. So we have our outcomes of Gaussian elimination that we know. I'm going to do these EROs pretty quickly, guys. So just kind of don't worry about all of the minutia of the EROs. I'll try to not make any mistakes here. So if I take the negative of the first row and I add that to the second row, I'll get 0, -3, -6, and then I'll get y minus x. And if I take -3 times the first row and add that to the last row, I'll get 0, -2, -4, and z minus 3x. Okay. And now I'm going to take, let's do another matrix operation. I'm just going to take the middle row and multiply it by -1/3. So 0, 1, and 2. And then this will become x minus y all over 3. And I'll recopy the bottom row the same way. Almost done here. So we end up with this matrix here, and now I'm going to do one more thing. I'm gonna leave the first row alone. I'm going to leave the second row alone. So that second row, notice I'm doing the ERO in the far right column as well. And now I'm going to take 2 times the second row and I'm going to add it to the third row, right? If I take 2 times the second row and add it to the third row, look what happens. I get something over here that I don't even want to write down. 2 times the x minus y over 3 added to z minus 3x is some alphabet soup of x's, y's, and z's, right? But it's basically going to be a pivot, my friends. Because what's going to go in this corner is not going to be 0. It's going to be some alphabet soup of x's, y's, and z's, yeah? If I'm making any sense here. And what does this mean over here?
No solution.
No solution. No solution, and so is this a spanning set for R3? No. It is not going to be a spanning set for R3 because we tried to take X, Y, Z and write it using our 3 vectors, and we did not succeed. We were unable to solve for C1, C2, and C3. See? I know I have only 30 seconds left, but I'm gonna make 2 really important points here. Okay, so hang with me for just an extra minute, and then I'm gonna make a video to show you a few more examples. First of all, do you see these 3 vectors showing up anywhere over there? The original vectors from the original problem, do they end up sort of appearing somewhere in the work that we ended up doing later? Do we see 1, 1, 3 over here anywhere?
Column.
The first column. Ooh, interesting. 2, -1, 4 is in the second column. And 3, -3, 5 is in the third column. So my first of my 2 important points is you didn't really need to do all, you don't, from now on, you don't need to do all of this. You can just kind of jump to the matrix. You don't even need to do this. Okay, you can just lay your vectors into the columns of the matrix. So the original vectors are here. Original vectors in the columns. That's my first comment. I'm gonna make a video and I'll go a little slower in my video with this, but I have one more comment. My second comment is, does it really matter what is going on with these tweaks that happen in the far right column? In other words, instead of calling these X, Y, and Z, if I just said there's some expressions here, and then I'm gonna do some EROs and the expressions are gonna change, but I don't really care what they become. I know that what's going to come up on all of these far right columns is just gonna be an alphabet soup of X's, Y's, and Z's that are not going to just go away to 0, right? So this, I know that these far right column entries are gonna get tweaked up from just the original X, Y, Z into some other more complicated expressions. But all that I really need to know is that whatever that is in that far right column is not going to be a 0. It will never be. And so you don't actually have to work very hard with that. With the far right column, you can just put these number symbols and just treat those as pivots. Treat those as pivots. You don't have to do the ERO very carefully to get the answer. So those are 2 quick comments. I am going to make a video, guys. I'm going to require you to watch it, but I hopefully will have made your homework life a little easier for tomorrow night as well. So thank you for today. I hope it's making some sense. We'll talk more about this next week. Bye for now.
So did you know that there was gonna be no solutions from the start, or is it just because you canceled out the bottom row?
I only knew, it's not because of canceling out the row, it's because, I did not know from the start that this was gonna be a no. I only knew it after I did all the EROs and I said, oh, I have a pivot in the far right column. That's the key.
But if you didn't get a pivot in the far right column,
If I didn't get a pivot in the far right column, then, if this had, for example, if this had, for example, turned out like that, then you would have said yes. And it would have a solution. Yeah, I need to talk more about this. I'll make a video that has a little more help with this
Okay.
stuff. Yeah, okay, great.